Okay, now I've been spending time on time-dependent problems, but always from the point of view of we have some PDE, we spatially discretize it, we get a system of ODEs, like y prime equals AY, and then how do we solve that using time-stepping methods for ODEs? But today we're going to look at a specific PDE and look at the whole process, discretizing in space and time. So it's a very simple PDE. One-way wave equation. Even though it's a simple problem, it's one that gives you ideas, the sort of things that can go wrong when performing time stepping. Okay, so the problem that we have here is B equals C UX, where C is a constant. And we have some initial condition. And we actually know the exact solution. It's just the initial data evaluated at X plus CT. So whatever the initial data is, the solution is just going to be that initial data shifted to the left at the speed indicated by the constant C. We're assuming here that C is positive. Otherwise, it would be shifted to the right. Now, you'll notice that I've not said anything about a boundary condition. Now, when we discretize, we're actually going to need one. But because the because I also haven't specified a spatial domain either. If I were to limit this to, that's what we have right now. This is a free space problem that wouldn't have a boundary condition. But if I limit myself to a bounded domain, then there should be a boundary condition. But really, because the data is propagating to the left, at least physically, it really only makes sense to have a boundary condition on the right boundary, as opposed to the left. So, but when you go to solve this numerically, what you need in terms of the boundary values depends on how you discretize this du dx right here. When you approximate the derivative at a certain point, are you going to be using values of solution at that point and to the left or to the right? And whether you do that dictates what sort of numerical boundary conditions you're going to need to impose. And that actually leads to what? Oh, sorry. Yeah.
You said that we only have a boundary condition on the right.
Physically, that would as well make sense, just because you have a wave that's propagating to the left.
One way.
Yeah.
Oh, so it's only okay.
Yeah. So you need some sort of input to keep the wave going.
So it goes on just.
Yeah. Yes. Yeah. Okay. But we're going to see, because of that direction of propagation, you have to be careful about how we discretize du dx and what information it's using to compute for derivative. Okay. Because like before, like Poisson's equation, we just use what was accurate. You use a center difference because of the symmetry, and we get a higher order accuracy. But that's not necessarily the best way to go in this case. All right. So, to describe finite difference scheme, and we'll see a few of them. For capital U, J, N, I guess there's not much difference between capital and lowercase u's on the board as opposed to my notes. I guess I'll just have to make my capital U's really big. That's approximation of the exact solution at X, J, Tn. And we'll let xj is x, n is n delta t. All right. Now, so I can just actually describe three schemes at once, but they all use the same approach to the time derivative. So for time derivative, we're just going to use explicit Euler. J plus 1 minus UJN over delta T. So this is corresponding to du dt is equal to the constant C. And then write out three different approximations for ux. So we have, so one of them is a forward difference, uj plus 1 minus n over delta x. And then we have a backward difference, ujn minus uj, j minus 1n over delta x. I was going to fill up room. And then the last scheme is the center difference over 2 delta x. So all of these various approaches to approximating du dx. Now, previously I've referred to these as forward difference, backward difference, center difference. Well, this one I'm still going to call a center difference. But now because we're talking about one-way wave propagation and to the left, the other schemes actually have different names. This one is called upwind, and this is called downwind. Okay. Now, okay. So, if we consider that the wave is propagating to the left, here, forward difference, because we're trying to approximate du dx at the point xj, and we're using information that's to the right. That's the information that we have about the wave. As opposed to downwind, this uses information that's to the left. That's where the wave hasn't been yet. So physically, intuitively, not such a good idea. And we'll see just how bad an idea it is soon enough. Now, the thing to keep in mind, though, is these are only upwind and downwind because we're going to the left. If I had made this ut equals minus cux, so propagation to be to the right, then these will switch. This would become downwind and this would become upwind. So upwind uses information about the wave so I'm having a little difficult time describing this in words, but okay, that using information from where the wave has been, as opposed to where it's going. All right. All right. Now, so now that we have these three schemes, we need to look at how they behave in terms of accuracy and stability. But first, any questions about what's up here before I? Okay. Actually, the upwind scheme is one that is to be implemented in the homework. Okay. So now we're going to look at the local truncation error. Okay, and what I'm going to do is, well, okay, for all three. What? Yeah, but the music. Yeah. All right, so for upwind, it's a forward difference, so you're looking at U of X. Oh, wait a minute. Okay. These be written in a slightly different order, but in the notes, but that's okay. So this is a forward difference. That would be equal to ux plus 1/2 uxx delta x plus 1/6 uxxx delta x squared, and more terms that are ordered delta x cubed. This is just from Taylor expansion. That you Taylor expand u at u x x plus delta x, and that's what gives all of these terms, and then dividing by delta x. So that'll be important for us for the upwind scheme. Now, if I replace delta x by minus delta x throughout, that would give me the local truncation error for a downwind scheme. I won't bother writing out here. The centered scheme. Let's do x plus delta x e minus u x minus delta x e over 2 delta x. Okay, so that's going to give me x, and then this is second order accurate, so we're going to have 1/6 u x x x delta x squared plus more terms that are order delta x to the 4th. If you're going to Taylor expand both of these, what will happen is, for instance, the terms involving uxx will cancel. Actually, any terms involving even order derivatives will cancel, which is what gives us a second order accuracy. And then for our time derivative, we only are using one approach here. It's a forward difference in time. Okay, and that's the first order accuracy. So that's going to be very similar to what we have here for the forward difference in space, except that instead of x, we have t. In fact, other than that, it's exactly the same. So the ut plus 1/2 utt delta t plus 1/6 uttt delta t squared plus order delta cubed. Okay. now the upwind scheme would have this approximation to DUDT equal to C times this approximation to DUDX. So to find the upwind local truncation error, we have the error for UT. Well, okay. So what you do is, remember a process for finding local truncation error. So you substitute the exact solution U of xt into the scheme, and you add a term I'm calling tau. That's the local truncation error. So when you do that, you're going to have exactly this from a time derivative. You'll have exactly this from a space derivative, all multiplied by c. So from a Taylor expansion, this is what you get. You get your error in time. Oops, forgot the delta t's. Plus 1/6 u t delta t squared plus order delta t cubed equal to c times the truncation error from our approximation of ux. So we'll fill all that in. Delta x squared plus order delta x cubed plus tau. And tau is the local truncation error we're solving for. So the idea is we want to solve for tau. Now, u is the exact solution. That means that ut equals cux. Most terms cancel.
This thing apply for also the second term,
What?
also the second term?
Oh, this and, well, we can't be careful about that because, if, so UTT is equal to UT with respect to T, but, UT is CUX with respect to T. So that's CUT with respect to X, so I can switch that. But UT is CUX, so we get C squared UXX. So in other words, differentiating with respect to T is equivalent to,
C squared of the.
yeah, so each differentiation gives another factor of C. Okay. So these two terms go away, but now, if I solve for tau, so tau turns out to be equal to, okay, so I have, okay. So if I replace this UTT with C squared UXX, then this is what I get. All right, so I get 1/2 CUXX times C delta t minus delta x. Okay, so that's the leading error term. And then I could keep going. I could say UTTT is C cubed UXXX. So I can write everything in terms of derivative with respect to x. So then I get C squared delta t squared minus delta x squared. Okay. And then it'll be additional terms plus order delta x cubed and order delta t cubed. Okay.
Does it change anything if we do it in terms of t?
Well, the expression would be equivalent. Okay. All right. So the order of accuracy of a method okay, depends on let me make sure I have this right here. Yeah. So the order of accuracy of a method depends on whether these factors that we have here are 0 or non-zero. Because we're free to set delta t or delta x. So, okay, unfortunately I've run out of room, but okay. So method is first order if the quantity R, which is equal to C delta T over delta X, is not equal to 1.
R's the residual.
No. Okay. Beware of a very common notation trap for students that once a letter is associated with a certain term, it seems to be bound to that term for all time. We are in a difference. I see it happen all the time.
I'm not the only one.
Yeah, definitely not. Not like if I use letter U, students always think U substitution. It's like we're not even doing integrals. So, yeah, and we're not doing AX equals B here. So, because this is equal to R minus 1 times delta X. So if R is not equal to 1, then the leading error term is proportional to delta X, so that's first order.
Condition.
Yeah. Yeah, so this is equivalent to R minus 1 times delta X.
Okay.
Yeah.
If it's R.
The thing is, if R equals 1, of course, this term goes away. Although that would mean that this term would go away too. And I can't help but think that actually all the terms would go away. At least as long as enough continuous derivatives exist. So does that mean we're getting the exact solution if R is equal to 1? Well, you can check it on your homework. So, okay. So, yeah.
Keep dreaming.
Yeah. So, but at least it's definitely first order if R is not 1. Okay. All right, so any questions about what happened here? Okay, now, if I were to do the same thing with the downwind scheme, where certain terms would have opposite signs, I would get a similar result. It's just that then the condition becomes R equal to -1. Okay. Now, okay, I'm going to summarize here. Okay. So upwind. Or if R is equal to 1. Downwind. First order if R is not equal to -1, which seems strange because that would mean that one of these quantities, C or delta T or delta X, should be negative, which doesn't make any sense. So right over that's the first indication that we have that the downwind scheme is not going to be a good idea. And then for the center scheme. All right, so the local truncation error there is tau. Using the same exercise, like you plug in your Taylor expansions and you have the error expressions from them, and simplify as much as you can, and you get -1/6 d u x x x delta x squared plus 1/2 c squared u x x delta t plus other terms that are order delta t squared or delta x cubed. So it is second order in space, which makes sense because we're using a center difference as second order. First order in time also makes sense because we're using a first order time stepping scheme. And it doesn't matter what R is. So second order in space, first order in time. Okay. Okay. All right, now, stability analysis. I'm going to focus on the upwind schemes. That's the most interesting one. This will be something I mentioned last time. Von Neumann stability analysis. Okay, now I'll repeat the upwind scheme so you can see how the von Neumann analysis works out. So the upwind scheme is Jn plus 1 minus Jn over delta t, C Uj plus 1 n over delta x. So using the substitutions for von Neumann, Ujn plus 1, that is our growth factor G. Jn is replaced by 1. And then Uj plus 1n, that is e to the I theta. Then Uj minus 1n is e to the minus I theta over delta x. Okay. Okay. Where theta is equal to k delta x. And keep in mind our initial data is e to the I kx. That's the basis for von Neumann stability analysis. That's what leads to all this. Okay. So now I can take this equation and solve it for G. And I won't go through all the algebra here, but what ends up happening is G turns out to be equal to 1 minus R plus R e to the I k e to the I theta, where R is the same as defined before, C delta T over delta X. And you can see that because if I were to multiply both sides by delta T, I would get C delta T over delta X, which is R. Oh, I just totally wrote something wrong here. That's not e to the minus. This is wrong. It's not e to the minus I theta, it's 1. Yeah, because, oh, this is wrong. This is a center scheme. That's what, okay, this would be UJN. Okay. Yeah, and UJN is 1.
That's what I thought, there was no 2 in them.
Yeah. Okay. Yeah, so that was the first clue. Something was off here. Okay. Whoops.
It actually will just show.
Okay. No. Yep, okay. All right. Now, we need to see where absolute value of G, like, is it, can it be greater than 1? We need to be less than or equal to 1. Okay. Now, if I were to work out the absolute value of G squared, so that's going to be real part squared plus imaginary part squared. So the real part is 1 minus R plus R cosine theta. And then the imaginary part is going to be R sine theta. So then if I expand all that out, it's a bit of a mess, and simplify as much as I can, I get 1 minus 2R plus 2R squared plus 2R, 1 minus R, cosine theta. Okay.
Ah, square. Oh.
Right. Now, everything you see here is a constant, except like theta is k delta x. K is variant because k can be any frequency at all. But if I want to find out how big it can get, I can think of this as a function of cosine theta. I think of cosine theta itself as a variable. So I think cosine has to be between -1 and 1. So I can think of this as finding a problem like that you learn about in Cal 1 for finding the absolute maximum and minimum on an interval. In this case, so if I call this X, actually I shouldn't use X. I'm not using W, I'll call this W. or W is between -1 and 1. So I can think of it as a function of W, and like, take a derivative, set it equal to 0, plug in the endpoints, all that stuff you learn to do in Cal 1. And this is what I find. That's the extreme values that are actually assumed at the endpoints are 1 and 1 minus 2R. And I need to make sure that these stay within the interval -1 to 1. So I can conclude that the scheme is stable. The scheme is stable if R is between 0 and 1. So that's what we need. Okay. In other words, it is conditionally stable. Now, I could carry out the same process with the other two schemes, downwind and centered. If I do, what I find they're both unstable. Doesn't matter what R is. I mean, no matter what R is, you can always find some value K that causes this growth factor G to be greater than 1 in absolute value. So those schemes are useless. And it makes sense physically that they should be useless because they're approximating dx using information about the wave that's not available. It's looking past where the wave has gotten to. So when you have this one-way wave propagation, you really should use an upwind scheme. There's some more information in the notes about like the actual expressions that were obtained, like in case you want to practice fundamental stability analysis and see if you get the same thing. But the general idea is the same, that you think of it as a function of cosine theta, find the absolute extrema, and see where, making sure that these stay within the interval -1 to 1. Okay. Now, any questions about this stability analysis? Okay. The rest of the time will be devoted to fixing the center scheme, because we'd like to be able to use the center scheme just because it's second order accurate in space at least. And fortunately, there is something we can do to get a viable method. All right. So what we do is next we solve a modified PDE. P is equal to C ux plus theta uxx. So we have like this artificial diffusion term. And then we use a center difference for that. also, so the scheme that we'll have is same as the previous centered scheme at first. And then familiar center difference stencil second derivative. The key is to choose the value of theta that will work in terms of making sure that the method is stable. Okay. I should mention though that if what I could do is rearrange this. And what we get is the original center scheme. Except instead of UJN here, we replace UJN by a weighted average involving points that are the neighboring points. So instead of simply having UJN here, we have we have a linear combination of UJN and its left and right neighbors. And look at the weights. Lambda over 2, 1 minus lambda, where lambda equal to 2 delta t beta over delta x squared. So, yeah, so this is a weighted average of values of u near xj. Yeah. That just comes from taking these terms and moving them to the other side. Okay.
Could you give a second? Just need a minute.
Okay. Now, but how do we still have to choose theta? So here are two possibilities. First is called the Lax-Friedrich scheme. And yes, it's the same Lax who from the Lax equivalence theorem. So for Lax-Friedrichs, you set theta equal to delta x squared over 2 delta t, which is equivalent to setting lambda equal to 1. And that has the effect of eliminating UJN from the scheme. So in fact, the method as a whole can be drastically simplified if UJN plus 1 is equal to 1 plus R over 2 UJ plus 1N plus 1 minus r over 2 uj minus 1n. So the value of solution at the new time is equal to this convex combination of u at neighboring points from a previous time, where r is the same definition that we've been using, c delta t over delta x. Okay. So that's quite efficient. So you get solution to the new time by multiplying the solution to the old time, but by a bidiagonal matrix, where the upper diagonal is 1 plus r over 2, the lower diagonal is 1 minus r over 2. Well, for purposes of a homework, I'd find if you're still using this form, because you'd be implementing something like this for the upland scheme anyway, and you know how to make a matrix for second derivative, because you've been doing it in all the other problems. So you can just use that here, and then similar for first derivative. And then like with whatever value of theta you need. So that might make things easier homework wise, but
Two?
what?
Oh, no, okay, no, so theta is depending on what we choose for the sets,
Yes.
delta x and delta t.
Yeah, so this value of theta gives you Lax-Friedrichs.
And we get to define delta t.
Yes. Okay.
Okay, I just did this one like with you before.
Yeah. Okay. All right. Now, this is for the accuracy. So it's order delta t, the first order in time, second order in space, which is what we also got for the center scheme, so that part's not any different. And it is conditionally stable. So adding this diffusion fixed fat problem for center scheme. The value of G is, okay. IR sine theta plus cosine theta. So if R is equal to 1, this has absolute value of 1. If R is less than 1, then it'll have absolute value less than 1. But so you need R, it's still need R between, well, actually R equals 0 makes no sense. So for implementing a scheme, but so same stability condition as we had for upwind. Okay. All right, so that's one approach to setting theta. The other approach is Lax-Wendroff. Okay, so for Lax-Wendroff, what we do is we set lambda equal to r squared, but that's equivalent to theta equal to c squared delta t over 2. Now, one thing I want to point out about both choices of theta, if you have delta t and delta x being proportional to one another, like some fixed value of r, and as you let delta t and delta x both go to 0, theta is going to 0, which is what you want, because as delta t, delta x go to 0, this modified PDE should converge to the original PDE. Otherwise, you're just really solving an entirely different problem. So that's one thing to keep in mind. All right, so with this choice of theta, what's the goal here? Because the goal of Lax-Friedrichs was to basically eliminate UJF to get a simpler scheme like that one. The goal here is to make a method that is second order accurate in time and also second order accurate in space. Okay, so So that's why we choose theta this way to get that. Okay. And it's done in the notes to work out the local truncation error and show that it really is second order accurate. The G, the growth factor, is 1 minus r squared plus r squared cosine theta plus IR sine theta. And it is less or equal to 1 absolute value with the same condition on R. Must be between 0 and 1. So again, conditionally stable.
Is that G?
Yeah, it's G.
Sine theta, is it absolute value of G the same?
Oh, all of these are just G, plain G.
No, one in absolute value.
I'm not sure what you're.
The sine theta, the very last equation after sine theta
Oh, this is absolute value.
of G.
Yes.
Okay.
Yeah. Oh, it didn't look like a G. Or okay. Okay. Oh, I think I might have a mistake in the notes. Yeah, I do. Okay. All right, questions about any of this? Okay, I want to show you, I wasn't sure if I would have time, but it looks like I do.
Okay, so
Uh,
can you please go back when lambda is equal to r squared,
yeah,
then theta is equal to c squared delta t on 2.
yeah. These are equivalent conditions just because lambda is defined in terms of theta this way.
Yeah. Okay.
Okay, yeah. Yeah, because for this to be r squared, you need another factor of delta t, and you need to get rid of a 2. Yeah. Okay. Okay. Other questions? Okay, so local truncation error for Lax-Wendroth. Now, here's the funny thing. Back in 1992, I took a class like this one. And learned a lot of finding different schemes, mostly unspectral methods, so similar material. And I have vague memories of these schemes, but especially Max Friedrichs and Max Wendorf being covered. And back then, I don't recall having any understanding of what they were about, like what I've just shown you. Now, if this doesn't stick with you, it's okay. It obviously didn't stick with me either, but I don't remember. Unfortunately, the textbook that I have, I often like loan books to students and never see them again. So it's out here somewhere. I just don't remember being explained like that, but, oh well. So, local truncation error or Wendorf. All right, so what you have is uj plus 1, uj n plus 1, n plus 1 minus uj n, t equal to c. Okay, actually, I need to write this term for the exact solution. U j e n plus delta t minus u x j e n over delta t equal to c u x j plus delta x n minus u x j minus delta x n over 2 delta x plus value of theta, which is c delta t squared over 2. And we have u x tn minus 2 u j tn, to run out of room, minus u x j minus delta x tn all over delta x squared plus tau. Can't forget that. That's what I want. Okay. Now,
Been reading this.
oh,
So
oh,
just because it misplaced a comma.
oh, oh. Also, writing's pretty sloppy.
No, but I fixed it. I've been reading with xj delta x.
Oh, okay, yeah, that would be weird.
What are you thinking about? Is that a plus the last one?
Whoops, yeah, this should be a plus. All right. Now, this equal to t plus 1/2 t squared, no, 1/2 u tt, which as we saw earlier is equal to c squared uxx plus 1/6 u t delta t squared plus 4 delta t cubed. Then for a first derivative approximation, we have 1/6 C U X X X delta X squared plus or delta X cubed. And then for the, and then here we have, oh, and this is C is coming from down here. But here I have C delta T squared over 2 times, oh, wait, up and down a term. This should be CUX plus all that. Okay. And then here we have UXX plus 1/12 UXXXX delta X squared. Mistake in the notes there. Okay. Plus order delta X to the 4th. Okay. Now, this use the exact solution. So UT equals CUX. So those terms cancel. And then, okay. Now, if I look at this term over here, I have, oh, there's something missing here. Oh, sorry. This term needs a factor of delta t. But UTT is equal to C squared UXX. So this whole term is equal to 1/2 C squared UXX delta t. But then I go over, oh, oops, I totally got this wrong. This is C that's squared, not delta t. So sorry, I don't know, both lines that needs to be fixed. C squared delta t. Okay. So now, if I look at the leading term we have here, what do I have? 1/2 C squared UXX delta t. They match. So this term cancels with this term. So then when I look at what's left, well, my leading error term here is order delta t squared. My leading term here is order delta x squared. And then my leading term here is delta t times delta x squared. But generally we have delta t proportional to delta x. So that's kind of like order delta x cubed. So really the leading error terms come from here and here. They're both second order. So if I were to rearrange all this and solve for tau, you get leading terms being second order for both space and time. But I want to show you why that happens because of the particular choice of theta that we use here. That leads to this UXX term canceling with the one that comes from here. Okay. Yes. Yeah, they have order delta t squared here or delta x squared here. And as long as we're using center differences, we're always going to get second order in space. It's just that we need to do something about this first order error term in time and get rid of it. And adding just the right amount of diffusion made that happen. Um, and then as for stability, making usual von Neumann substitutions throughout this. So we have G minus 1 over delta T equals C over 2 delta X e to the I theta minus e to the minus I theta. Then I have C squared delta T over 2 delta X squared. And then we have e to the I theta minus 2 plus e to the minus I theta. But then if I were to multiply both sides by delta t, I get g is equal to 1 plus r over 2, and then this right here is 2i sine theta, and then I get r squared over 2, and this turns out to be 2 cosine theta minus 2.
2 cosine squared theta.
Um,
2
well, oh, okay. Actually,
Yeah, I just did this.
okay. Um, okay. Okay, so we get 1 minus r squared plus r squared cosine, which we're abbreviating as c, plus I r s. S is the sine theta. Just to abbreviate. Okay. So then this right here, that's the real part, and rs is the imaginary part. So what I do in the notes is I work out the absolute value of g squared, so real part squared plus imaginary part squared. It's a bit of a mess, but you can apply the same idea that actually you can express the whole thing in terms of just cosine, and then treat it as a function of cosine and find out where the extremes are. And the extremal values are 1 and 1 minus 2r squared. So extremes of absolute value of g squared, 1 minus 2r squared. So that's what shows you that as long as r is between 0 and 1, it works out fine. And you get stability. And now I'm totally out of time.
We have to find the,
Yeah.
process.
Yeah. Mhm. So I've come to the end of the notes. So there's nothing left but to get the dang homeworks in. Also, I need each of you to let me know about scheduling for review oral final part, either for week after Thanksgiving or the following week, which is finals week, somewhere in there.
What's the, when can you start?
After Thanksgiving,
So 28th.
Eighth. yeah. Okay, and get that coding done, dang it. So, like, get all the coding done.
Possibly the end of my.